Students, welcome to lecture number 24. So, we have been discussing about different types of machine learning algorithm, and I told you that we are going to move into the deep learning aspects of this in the materials engineering. But before that, let us also finish something which we need to be told. So, today we will discuss major part of this lecture on unsupervised learning, and then we will at the end we will talk about some aspects of deep learning. And the next class onwards we will discuss different models of deep learning and how they can be implemented. So, first of all, in the last lecture I talked about clustering, right, and in fact we have discussed a lot about clustering. Clustering is a part of unsupervised learning and it is used widely in material science engineering, in the sense that you can have data obtained from different sources to model some kind of a phase diagram, phase evolution, or even you want to predict mechanical or functional properties of materials, and this data will be such that you need to find a correlation among the data, and for that you need to use clustering. So, therefore, as a part of unsupervised learning, we know that this group of learning methods, they interpret data based on only input. In case of supervised learning, you have both input and output, that is what is called variable and the target values. So, in case of unsupervised, you have only variables, no target values, that means you have only input. So, for each input you do not have any output values, that is what you have work on, and many cases we have that kind of situations in material science engineering, and that is why these algorithms are very much important for you to know, understand and implement in real life situations when you will do this modelings of different kinds of behavior, prediction properties or phase diagram or phase evolutions, or even situations where you have less number of data, but you need to use it to predict some kind of a phase or microstructure. Therefore, do not only underestimate that only supervised learning is used in alloy design. Yes, it is used quite a lot, because regression, classification or even NN methods can be widely used in case of alloy design concepts or predicting properties of alloys or other materials, but at the same time unsupervised learning also can be used for this kind of predictions, exactly not the same way, but wherever you have problem of data or you have only input variables, you can use this. So, there we have different kinds of methods we already discussed, like KNN we have discussed couple of lectures or 3 lectures before. Then yesterday the last lecture we talked about k-means clustering and also hierarchical clustering. So, then we have also discussed about neural networks or ANN methods, but there are many more, like you have PCA, principal component analysis, independent component analysis, ICA, or you have also a priori algorithms and singular value decomposition methods. So, I will not get time to discuss each of these techniques, but it is all available in literature. You can get into books or even internet literature, understand that, but I am discussing only specifically few methods. So, clustering is what is the task of grouping data points. And how do you group? You group based on the similarity with each other, and that is what is called clustering or cluster analysis. This method is part of unsupervised learning, because you have only input data, and it aims to gain insights for unlabeled data points. Unlabeled again is another word which is used for data for which you do not obtain target values. So, the picture shows here at the bottom, you see there are 3 clusters present, but you can have many more clusters present actually, depending on your similarity index what you are looking for, but on a broad scale you can only have 3 clusters. You can see that we have grouped together, and this is the main aim is to form clusters or groups of homogeneous data points from a heterogeneous data sets. That is what is the aim is. How does it do? It evaluates the similarity based on a metric. It can be Euclidean distance, it can be cosine similarities, Manhattan distance, or then many other distances also. I have talked about it in one of the slides, and then it groups them based on this high similarity score together. that is what it is. So, it calculates the distance of certain kind of distance, either Euclidean distance, which you are more used to it in coordinate geometry. It can also talk about Manhattan distance or cosine similarities also. Many other similarity parameters exist. I have not put all of them together, but these are the more important. But most of us are more accustomed to it, or rather habituated with is Euclidean distance. So, based on this aspects, you can have two types of algorithm in clustering. One is a flat algorithm, and it basically starts with random partitioning, because you have you understand that you have heterogeneous data sets, you have to partition into different clusters. So, initially it starts with a random partitioning and then redefine it iteratively. K-means clustering is one such model, but you can also have hierarchical algorithms, because when you have problems in using K-means algorithm, because random partitioning may not work in some cases, and you may not have prior information about how these data points are connected, then you have to use hierarchical algorithms like at the bottom up or a top down or divisive approach. It is exactly same as like a nanomaterial synthesis I talked about in the last lecture. So, bottom up or top down approach, we will talk much more, but basically broadly putting together, these two are the main classification algorithms. Centroid approach, we guess a centroid first, a central point of any cluster, we assume that actually, and then assign point to the cluster based on the nearest neighbor distance. Remember, we talked about how to calculate distance, either Euclidean distance, Manhattan distance, or any other type of distance you can think about it, given in the slides which I have already discussed. So, you have to first find a center or central point, and that center is random, remember that. We do not actually assume the center to be fixed, we put a random center and then try to calculate distance from the center point to the points nearby, and whichever points have nearest neighbor distance to the centroid, we put them together as a cluster. But in hierarchical, so that is the main assumption in centroid approach. In centroid approach, you are assuming a central point per array, right, without assuming that you cannot separate the data. So, in a hierarchical approach, you begin with assuming each point is a cluster by itself. That means, if you have suppose let us say 1000 points, each point is considered as a cluster itself. That is the main difference between the centroid and the hierarchical approach. Once you do that, then what you do, you repeatedly merge nearby clusters, issuing some kind of a measure how close these clusters are, like distance, or they can how good a cluster the resulting group would be. Many other things are there, but starting point hierarchical clustering is that we assume every point is a cluster, and then we merge the nearby points to that cluster. And we can use various kinds of means. We can use distance as a means also. You can use also means of similarities based on some other parameters, like how well they are connected to each other, like in a. So, hierarchical approach will lead to formation of a tree like structure or dendron, and that is how these things are connected. It is like a family tree. So, therefore, these clustering approaches are widely, broadly speaking, used, but we can also talk about different means of algorithms like centroid based, we already understood what is it is. You can also density based clustering, how dense the data points are in a particular set or particular data set, how dense the data points are to a particular position, then you can cluster them. And as I told, hierarchical clustering is nothing but a connectivity based clustering. Lastly, you can also have distribution based clustering, like you can use some kind of normal distribution or chi distributions or any other distribution based, and that can be used as a clustering means to separate the data points. So, to talk about a little bit more in details, centroid based clusters basically are the most easiest clustering algorithm, all of you will use that. So, they actually group data point based on the closeness, their closeness of each other. So, we assume a centroid, a central point, and then calculate distance from central point to the nearest points, and based on the distance we can put them clusters. And I told you where distance can many things, like Euclidean distance, all of you are used to it, root over x square minus y x square plus y square, that is root over x1 minus x2 square plus y1 minus y2 square, right, that is what is called Euclidean distance. You can have a Manhattan distance or Minkowski distance also, and in case of density based clustering, they are actually based on the density of data points. So, as compared to centroid based, which requires number of clusters to be predicted and sensitive to initial data point as centroid, density clustering determines the number of clusters automatically, because this talks about the number of points per unit area or per unit volume, right. That is what the density is, and therefore, it is less sensitive to beginning assumptions or beginning positions. So, there are these are basically good at handling clusters of different sizes and forms, making them ideally suited for databases to regularly separate overlapping clusters. Remember, centroid clusters you do not actually do overlap clusters, but here you can actually do overlapping clusters also. Connectivity clustering is very simple, as I told you, it is basically hierarchical clustering. This method of assembling related data points into hierarchical cluster is called hierarchical clustering. Here each point is initially considered as a cluster, and then subsequently they are combined with other clusters, and so that we can form a similar lineage like in family trees. So, distribution as a very simple mention, it can be basically based on certain kind of a probability distribution function like Gaussian, binomial, G, any other distribution within the data points. And distances only, right, I will not talk much. This is what is your Euclidean distance, this is your Manhattan distance, this is your max distance or L infinity norm distance, whatever you want to use, you can use depending on your category of data. So, let us talk about what is the K-means algorithm. This is a part of first one is centroid based clustering. So, we take K cluster centroids. You can see here there are 5 points, and what do we do? So, we have suppose K is 2. So, K means which K is a number, K can be assumed anything 1, 2, 3, 4, 5, 6. Now, how do you do that? Basically, you simply put K is 2. So, one will be this cluster, one will be this cluster, right. So, you can put a centroid here, measure distance between this centroid and the data point, and then calculate the centroid and these data points, right. Similarly, you can put a centroid here, calculate distance, distance and distance, right, and put them into clusters. But you understand that initialization is very important. Initialization means is putting the centered, so that is a big assumptions. So, K-mean clustering assign data points to one of the K clusters depending on the distribution from the center of the cluster. So, that is what is center is assumed to be centroid, that is already placed. It starts with by randomly assigning the cluster centroid in the space, and then each point assigned to one of the cluster based on the distance of the centroid to the cluster to the points, right. And this perform best when data are well separated, remember this. If data are overlapped, this will not be a good one, remember this. Then you have to use density based clustering. And why it is used widely? Because it is very fast compared to any other clustering techniques, very fast. It provides strong coupling between data points, but it does not provide clear information regarding the quality of the clusters, remember that one. But hierarchical clustering or density clustering can provide much better information of the quality of the clusters. So, K-mean clustering is just like a, to be layman point of view, it's a rudimentary clustering technique. It is very fast, widely used, that is why, right. Shopkeepers data can be easily separated, which customer is buying which kind of products, what kind of shampoo they are buying, easily can be clusters using this kind of data. So, what are the issues here? First issue is that we have to pick points sufficiently far away from the centroid, right. That is a major problem is initialization. How do you put these centroids? Okay, I can put one way, you can put other way, somebody else can put the other way, right. So, as the computational progresses, one can decide to split one cluster, sometime you can merge when two to keep the total K constant, right. So, K is first assumed, give the example like K was 2. So, we can assume K, but K can be 3 also, right. A test whether to do it or not, that is the biggest question. So, how, having located the centroids of K clusters, we can reassign all points, since some points that are assigned early may actually wind up closer to another centroids as compared to that. That is probably one way of taking care of this. First you do random assignments of the centroids and then cluster them and then you can actually reassign some of the points to some other other clusters which they might belong to. The problem is that it does not provide any information of the quality of cluster, right. That is why this issue arises. So, now in order to take care of those problems, that is why hierarchical clustering came into picture. It is a connectivity based clustering technique, and here we assume every data point is a cluster, and therefore, then you actually try to find a similarity of the points based on some distance or some other means, and then assign them. So, in the process you have to draw a dendrogram or tree like figure produced from hierarchical clustering, and that will depicts very well the hierarchical relationship, like relationship between a grandfather to father to a son or a daughter is very clearly defined in a hierarchy, family hierarchy. Same thing is done here. So, individual data points are located at the bottom of the dendrogram, while the largest cluster, which may include data points, are located at the top. I will show you some example. I have already talked about, in order to generate the defined number of clusters, dendrogram can be even sliced at various sides, okay, like that. You see the subjects is what is the top, that is the largest cluster, right. It will include all data points at the top of the level, and individual data points are located at the bottom of the level, like agriculture, biology, physics, computer science, space, right. You can see then agriculture has dairy, crops, forestry, agronomy. So, these are the bottom level, and then your biology also same thing, physics also. Am I clear? This is taken from Yahoo. So, now we can actually talk about that if you want to generate different number of clusters, a dendrogram can be sliced at different heights. You can slice it here, the shown here, the 2 arrows. So, basically it builds a tree like structure, a taxonomy, that is why it is called a dendrogram, and this is very widely used recursive applications of for applications of a partial clustering algorithm, widely used. Okay. So, dendrogram is like this, you can see here it is currently this is your top, this is what is at the end, and they are like a tree like structures. Now, there are two types of these hierarchical clusterings, you have to understand that. One is called agglomerative clustering or top down clustering, and the second one is called divisive clustering, what is called a bottom up clustering. So, what is that agglomerative clustering or HAC? This is known as a bottom up approach. Okay, sorry, this is a bottom up approach. I think I told you wrong. Agglomerative is a bottom up, divisive is a top down approach, like a nanomaterial synthesis we talked about, right. If you go back to the synthesis of nanomaterials, either it can be top down, you can take it chalk, break it down into small pieces till you achieve nanoparticles, or you can start with the atom and build on structures, that is called a bottom up approach. So, this is what is done. A structure is more informative than unstructured set of clusters written by flat clustering, that is what is your k means clustering is. This clustering algorithm does not require us to specify the number of clusters, that we have already told you. So, this algorithm treats each data as a singleton clusters at the outset, then successively agglomerate the pairs of clusters until all clusters are merged into a single cluster that contains all the data, that is like a dendrogram. Now, on the other hand, in case of divisive clustering, what it does? It does not require also need to specify your pre-specified number of clusters. This requires a method of splitting the clusters instead of joining together, splitting the cluster that contains the whole data. So, therefore, in top down you are basically what is that? You are slicing the data, or basically you are doing the splitting the data, that is what you do. In case of bottom up approach, you are putting them together, that is what is important in this case. So, HAC starts with each dot in a separate cluster, then they repeatedly join the closest pair of clusters, and history of merging this forms a binary tree, right, very simple. On the other hand, divisive clusters, it partitions data into two groups first and then does this recursively, iteratively, that is what it is done. So, we will not talk about much more things, but at the end I want to show you the different distance matrices. I know we only talk about Euclidean in our when you do mathematics, but there are many such like Minkowski, Canberra, you can see here, no, Chebyshev, quadratic, Moulin-Biss, it is by name of the Indian scientist P.C. Moulin-Biss, correlation based on certain kind of probability functions, chi-square, kernel rank, there are many more actually. So, I just given you some charts, and this is very important, you can use one of these. So, now once, so therefore, I just wanted to give a detailed description of this, that is what I took about 15-20 minutes to describe the different kind of things. So, today we will talk about another important algorithm, which is called EM algorithm, and this is also important algorithm for unsupervised learning. And this is used to find maximum likelihood parameters of any statistical model whose expectation can be shown directly. As you see here, it is a algorithm which can be used to handle situation where some variables or features are partially observable or rather missing, right. Suppose let us say you have variable data, some value are missing, how do you correlate them? So, certain variables are observable, we can use them these instances to learn and estimate their values. Once you learn, then we can predict the values those variables which are not observable, right. It is very difficult to give an example of this. In real life situations, you will find there are many kind of phenomenon happen in which, or will be happening, in which there are a lot of features or a lot of variables which are directly not visible, but output is visible, right. Something is happening, you can see that, but what are the factors controlling that output, all of them may not be visible. Sometimes it is not possible even to collect data from that experiments which can signify how many number of variables, how many number of features are available. So, how do you do that? In those situations, this algorithm works nicely. This is why this algorithm I wrote correctly, it applied to latent variables, latent heat, right, which is not seen or not observed directly, but it is there. Similarly, this is applicable to latent variables, which are variables that are not directly observable, but inferred from the value of the observed variables. Many times you do that, right. Many times we infer some variables from our calculations, we do not see this variable at the beginning. So, in those cases this algorithm will work nicely. Now, listen carefully. So, how do you do that? So, basically it is by leveraging a known general form of probability distribution. It can be any, it can be Gaussian, it can be Chi distribution, it can be a binomial distribution, you can take any of them which can govern these latent variables. EL algorithm then predict the values of these variables very accurately, but since some data are missing, how do you do that, right? That is what, then how can you form a distribution functions? Fine, whatever value available to you, you can form a distribution functions, and using this distribution function you can basically predict the other ones reasonable accuracy. EL algorithm is commonly used for all random variable models and even can handle, this is important, missing data, remember this is very important. So, this is what is the basis of EM algorithm. Now, it has two steps, one is called E step, in which algorithm computes the latent variables, expectation of the log likelihood using current parameters estimate. So, we will talk about a little bit. Second step is called M steps, this is where actually it does maximization, maximize the expected log likelihood obtained in the previous steps, right, and then the model is parameters are updated based on that. So, let us try to understand it a little more, what is it. So, and as I hope you understood that this was proposed in a very important paper in 1977 by 3 scientists, Arthur Dempster, Nan Laird and Donald Rubin, and this particular algorithm become very famous because it is very useful in statistical modeling and estimation. And as I said, this is applicable to all latent variables, which are variables that are not directly observable, but inferred from the values of the observed variables, that is what it is. So, let us talk about little bit more on these aspects on the board, and this is actually also called a probabilistic algorithm. So, this is also called a probabilistic algorithm. So, EM estimation right. What EM stands for? Expectation, not estimations, I am sorry, expectation maximization. Expectation, right. Algorithm. And basically it is nothing but such is a maximum likelihood, such a maximum likelihood hypothesis. This is what is important. It searches for the maximum likelihood hypothesis. How does it do? By repeatedly re-establishing the expected values of the latent variables. Let us spend couple of minutes here. So, it searches a maximum likelihood hypothesis. Hypothesis is something which has no mathematical foundation, but it searches for that. And how does it do? By repeatedly re-establishing the expected values of the latent variables. As I told you, right, in real life there will be a lot of problems where you have some variables which are not seen observable, they are called latent variables. And if you want to find the values or predict the values of those latent variables, this is the best way. So, let us call these latent variables as Z I j. Okay? Let us call that. Now, once you do that, so what is done? There are two steps actually, as I told you. Z I j is measured or found out using some current hypothesis. Any hypothesis means some formula. Okay. It can be some distribution function, it can be some algebraic formula. This latent variable is found out using that. It is a random choice. Okay. You can choose any, you do not have to worry about what is the particular process is, you can choose that. Okay. And this hypothesis is, let us say H, and we can write down H as like this mathematical form, H equal to mu1 and mu2. Okay. That is what it is. It is basically this latent variables initialization, remember this, is found out using some current hypothesis, correct. So, that means H is a function of mu1 and mu2, and what kind of function it is it's up to you to decide. It can be algebraic function, trigonometric function, it can be even distribution function, that is your choice. So, and there mu1, mu2 are arbitrary initial data. Initial data. So, then this is what step 1 is. Then what does it do? Then iteratively re-establish H, iteratively establishes re-establishes, not establishes. Okay. Let us try it properly. Some of you might be taking notes. re-establishes h by h is a function which we assumed initially based on initial data, but that was based on certain current hypothesis or current function. Now, how do I do? Iteratively h by iteratively establish h by calculating E as a function of j. E is expectation, that is your expectation. Okay. E of j of each latent variables assuming hypothesis. Okay. So, this will iteratively establish h. You can do lot of loops h by calculating E j, expectation of j, that is E j of each latent variables by using this, assuming this hypothesis. So, you have done that. Okay. So, what you are doing first? First is your, this is the latent variables, right, and these latent variables are found out using certain current hypothesis, correct. So, what you do then? After that, you iteratively re-establishes h, that h is the correct one or not. How do you know that? You have to iteratively do these calculations, that is a loop, okay, if and else loop probably, and then you do that by simply calculating this expectation function. That is the first step. And second, in this case of second one, okay, this is the most important step. You are doing expectation, calculating E j of the latent variables, assuming that hypothesis h is equal to mu 1, mu 2, right. So, you have done that. What is the next step you do? Now, calculate, this is very important step, calculate the new maximum likelihood new maximum likelihood. Okay. New maximum means what? So, basically you have to know that this is the correct or not, and in order to know that you have to maximize the values, right. That is what it is, new maximum likelihood hypothesis. This term sometimes may look like a Hebrew, but likelihood hypothesis is very widely used in mathematics statistics actually, and that can be h prime is mu 1 prime, mu 2 prime. Okay. I am writing in general, assuming values taken from the individual latent variables. Individual latent variable G I j. So, therefore, E I j, sorry, E not E I j, is basically E within bracket Z I j, that is equal to probability x is equal to x I, x is equal to x I. This is how it is written in statistics, x is equal to x I, mu is equal to mu I, divided by summation of all probabilities n 1 to capital N p x is equal to x I, mu is equal to mu I. So, here you are calculating the probability, remember expectation, probability of this point x is equal to x I. satisfying the current hypothesis divided by total probability, because you can have many current hypotheses possible, right, that is what. So, this is the main aspects of this algorithm. So, now one can actually use we can convert this equation to what do I say, convert the equation to normal distribution. E j can be converted to a normal distribution function very easily if you want. So, I can actually do that. So, let us remove this point here. So, this function what we have written here, this function whatever written here can be converted in terms of exponential minus, remember this, right, all of you should know that x I minus mu square divided by summation n is equal to 1 to n, right, exponential 1 by mu square x I mu square. So, if you convert this, if you use a normal distribution, this will look like this. So, what it is doing is calculating the probability distribution, right, total probability, summation probability and the individual probability, that is what it is doing. So, that is why it is find out the maximum likelihood that these points will belong to, latent variable points will belong to certain cluster. This is what is done. So, therefore, this is called E step and this is called M step, right, E and M, let us write that, E step and this is called M step. This is what you do. So, now let us come back here. So, important terms, first is it is doing the latent variables trying to probe, and what it is doing, it is taking likelihood. So, likelihood log means what, like nothing but a log of the likelihood value. I have, suppose let us draw that, suppose I have a point here and I am going to see whether this is latent variable points is belong to this or not, correct. So, I calculate the location of these points, right, although I do not know this because this is a latent, right. So, what I do, I calculate, I just try to with this point I try to find a function which is nothing but mu, let us say h mu by mu j, right, and then within this function I try to see whether this can also be part of this function or not. If it is, we reestablish that, if it is not, take another function and do that. And therefore, the expectation maximization tips I told you, and convergence is very fast here, very fast here, because of this algorithm itself is such a nice things. So, let us stop here. I think we have taken sufficient enough time to explain the expectation maximization algorithm. We will get back to you in the next part of the lecture.